Morning, everyone. I was thinking we could just recap briefly what we did last week. We had a pretty detailed look at the mathematical properties of so-called orthogonal transformations, which can be used to represent rotations in real space. And one of the key points that we discussed, I think in the final lecture last week, was that the time change of a vector depends on whether or not, or it will be different depending on whether you are in a stationary system or in a rotating system. So let's say we have some vector A, which in a stationary system can be written like this. Now, any vector can be represented in any coordinate system. So let's say we have a rotating coordinate system, a primed system. Where the same vector can be written like this, expressed now in terms of the axis of the rotating coordinate system, and also new components as well. So to understand why the time change of a vector will be different in these two coordinate systems, let's consider the time derivative of A. Which will give this when we write the A vector in the following way. And so I'm just considering a two-dimensional vector here for simplicity. You can extend this argument to 3 dimensions. So that's this part, but let's now consider the representation of this vector in the rotating coordinate system. Which will give us this, but not only this, there's an extra term. So this is an extra term, which stems from the fact that the unit vectors in this rotating coordinate system change with time, since it's rotating. So you can see that the time derivative of the vector as in the stationary system is equal to the time derivative of the vector as in the rotating system plus this extra term. And we derived a general operator relation which expresses precisely this fact. And what this equation tells us is that to find the time derivative of some vector in the space or fixed system, we have to consider the time derivative as seen from the body system, the rotating system, plus this extra term. And as a limiting case, we can see that this formula makes sense, because consider a vector which is fixed in the rotating system. In that case, the time derivative as seen from the body system is 0, which means that the time derivative of the vector as seen from the fixed system should be equal to its tangential velocity, for instance, if it's moving in a circle, which is precisely what you get here. So that's just a limiting case. So we ended by briefly starting on the Coriolis force, which can be derived from this. And what we did was that we used this operator relation on the position vector. So if you insert r, the position vector, sorry, in this operator relation, you get that the velocity as seen in the fixed system is equal to the velocity as seen in the body system plus this extra term. Okay, so we know that this makes sense. Now let's see what happens if we take this new vector and insert it again into the operator relation. Which gives us this. Now, to evaluate the time derivative of the velocity as seen in the fixed system, and then to take this quantity as seen in the body system, we have to express this velocity in terms of these vectors, which are seen in the rotating system. So the first term here is just the acceleration as seen in the fixed system. It's just dv dt in the same system. So we get as. And then we have this. The first term here is the time derivative of the velocity as seen in the rotating system evaluated in the rotating system, which means that it's simply the acceleration as seen in the rotating body system. So we get AB from the first term here. Oh, I'm sorry. It should be a time derivative here, right? Because it's the time derivative of Vs. So inserting Vs is this. Means I have to take the time derivative of Vb and also this. So I indicate the time derivative here by a dot of this entire thing. So let's assume here for simplicity that omega, the angular velocity characterizing the rotating system, is a constant. In that case, it's simply dr dt, which gives us Vb, plus we've assumed that the angular velocity is a constant. Now, what we're interested in ultimately from this calculation is to say something about how is the force acting on a particle as seen from the stationary system related to the force acting on the particle as seen from the rotating system. So we know that the force should just be mass times acceleration if we have a constant mass. So let's just multiply this equation with the mass of the object. where now Fs is the force acting on the particle as seen from this stationary system, whereas this is the force as seen from the rotating system. Okay, so this means the effective force acting on an object in a rotating system is given like this. So I just moved this term over here, and then also interchanged these vectors to get an extra sign change, so that's still plus. And then I also move this term over here. So you see then that we have two extra terms now. The effective force acting on the particle as seen in the rotating system is equal to the force exerted on the particle as seen from an observer in the stationary system, plus this term and this term. So let's now try to analyze these terms and see what they actually represent. And oftentimes when you find yourself faced with equations that you would like to interpret physically, what they mean, what the different terms represent, it's useful to consider limiting cases and just take one term at a time. So we see that we can get rid of this term by first considering a situation where the particle is not moving in the rotating system. So it's just following the rotating system. In that case, Vb is equal to 0. And so we see that the effective force is equal to the force exerted on the particle as seen from the stationary system plus this extra term. Do you recognize this term? So we see that its magnitude, if we just consider for simplicity a case where everything here is perpendicular, omega is perpendicular to r, so we have, let's say, some circular motion in a plane. In that case, the magnitude is m omega squared r. Any ideas? Yep.
Centrifugal acceleration.
Exactly. The magnitude here is equal to the centripetal acceleration required to keep the object moving in a circle. So here it has the minus sign, which means that it's acting in a given direction. So in the rotating system, this is actually perceived. If you were the object in the rotating system, this would be perceived by yourself as a centrifugal force, pressing you outwards. So say you're in a car, you're driving around in a racetrack in a circle, and if the radius is sufficiently small, you would feel yourself being pressed towards the door of the car. This is the centrifugal force. And so you see that in order to have a net force perceived by yourself in the car of 0, you would need a door pushing back in yourself. This would be the centripetal force required to keep you in the orbit. So then this would match the centrifugal force and you would experience a net force of 0. But an observer in the middle of the racetrack, say, he would see only this centripetal force acting on you, keeping you in this orbit. So you are perceiving an extra fictitious force, if you will, but for yourself it's pretty real. right? You will actually feel yourself being pressed towards the door. So this term the second term in this equation may be identified as the centrifugal force. So that was for the limiting case of where you are stationary in the car. So let's now try to say something about this term here. And so you may consider yourself moving inside the car. Perhaps that's a bit artificial. Let's say you're on a carousel. Okay, you're at the Tivoli, and then you have these merry-go-rounds, which we can assume have a circular form. And then let's say you're sitting on this horse or spaceship or whatever in the carousel, and then you're trying to move on the edge of the carousel as the carousel is spinning. That would correspond to a case where VB is non-zero, because even in the rotating system, you're now moving. So we see that in that case, we have an extra force here. So let's try to see if we can visualize this somehow. Here you are. And let's say you're trying to walk on the edge of this carousel, which is spinning. So let's say it's spinning like this, so the angular velocity points outwards. So VB crossed with omega means that there's a force F1 acting on you, stemming from this first term, pointing somewhere like this. In this particular case, where VB is pointing that way, it's pointing outwards. But let's say you're moving in some arbitrary direction, then F1 would still be perpendicular to the velocity and omega. And this is the Coriolis force. It's a force which acts on an object which is moving in a rotating system. I don't know if you actually tried this at some points. I did, and you can actually feel the force. It's pretty scary. You really have to find some good balance to be able to walk along the edge, because you feel that there's a very real force trying to push you. So you can try it if you want some time, unless the officer at the Tivoli stops you. I don't think it's allowed, but so one way to memorize this is that you will have two extra terms if you're in a rotating system. You will have one if you're stationary, but you will have two, one extra if you're moving in addition. So this Coriolis force actually is operant on Earth, right? Since we're moving on a rotating coordinate system. And it has all sorts of manifestations that can be seen in different contexts. It actually affects the wind circulations even. Because without the Coriolis force, the winds moving on Earth would just move along isobars where the pressure is constant. But this Coriolis force acts on the wind, since the wind is particles moving, and causes them to deviate from these isobar curves, for instance. So this is an important derivation from this particular chapter. Okay, we'll move on to the next chapter. So basically, whereas we so far have considered the kinematics of rigid bodies, sort of the qualitative motion that we could expect for rigid bodies, we're now going to have a more quantitative look at the equations of motions that describe this kind of movement. So as a preliminary to starting up this chapter, one thing that we need to convince ourselves of is that the angular velocity vector, which characterizes the rotation, say, of a rigid body, is descriptive for the whole rigid body. It's the same for all particles in the rigid body. And this may seem as a trivial observation, but it's important because this will feature prominently in the derivations that we will consider next. So if you have a rigid body of some arbitrary shape and you consider 2 points, 1 and 2, then the angular velocity of these particles have to be the same if it's a rigid body. Because you can consider the effect it would have if these points had different angular velocities. That would mean that you would have an actual deformation of the body, right? This point would move faster than this one. It would cover a larger angle than this one. So you would no longer have a rigid body. You would have some plastic body. So it suffices with a single angular velocity vector to characterize this rigid body rotation. Okay, in order to derive equations of motion, it's useful to consider physical quantities such as the kinetic energy and the angular momentum, since we know that the Lagrangian depends, for instance, on the kinetic energy. So we would like to find some way of expressing the kinetic energy through the least amount of parameters for this body, for instance. Well, to do so, we have to choose an origo somewhere. We have to choose a coordinate system. And a particularly good choice for this origo is the center of mass. It's a quite natural choice as well. So if we consider a rigid body rotating, we can consider it rotating around the center of mass. COM means center of mass. So let's now try to have a look at the angular momentum that the rigid body has around the center of mass. So keep in mind that whenever you're discussing angular momentum or torque or any such quantity related to rotation, you always have to specify in relation to what? The angular momentum with respect to some point, right? You have to have a reference point to specify what the angular momentum or torque is. So we follow our usual strategy of dividing the rigid body into several sub-regions. Like this, which may or may not have different masses, depending on if the body is homogeneous or inhomogeneous. So using the sum convention with the repeated indices, the angular momentum in total will look like this, where now mi is the mass of each little section that we divide the body into, ri is the relative distance from the center of mass to this point, and vi is the velocity of this sub-region relative to the center of mass. And to begin with, we'll consider the case of purely rotational motion around the center of mass, in which case we know that the linear velocity v can be written in the following way. And omega I is equal to omega due to this argument here. Let's insert that into L. And by simplifying this cross product, or rewriting it, depending on how you look at it, we can obtain this. So we're just using some vector identities for cross product. All right, so this is our general expression. Let's now try to have a look at the different components of L. So we'll dissect this and consider each component to gain some insight. So let's consider, for instance, Lx. From the first term here, we just have omega vector multiplied with this, so it becomes omega x multiplied with Ri squared. And this term translates to this. So if we now collect all the terms that correspond to omega x, omega I, and omega z, we find this. And so we see that from this expression, the angular momentum, the component x of the angular momentum, can be expressed as a linear combination of the components of the angular velocity. By observing that, we realize that we can write this as a matrix relation. Namely, we can write that the L vector, the angular momentum vector, is equal to some matrix I, large I, multiplied with omega vector, or in component form like this. And by comparing this general form with this explicit form for Lx, we see that the Ixx, or the I11, if you will, element of this matrix I is given like this, and the Ixy, or I12 element, if you will, is given like this, just by comparing with this expression for Lx. Now this matrix I is kind of important. It has a special name. We can call it the matrix of inertia. You may have heard of the moment of inertia in previous courses, so it's related to this. It's basically relating the angular momentum to the angular velocity vector, so that you can write each component of L as a linear combination of omega. And this has an important consequence, because, I don't know, when you think of the angular momentum and the angular velocity vector, do you usually think of them as pretty much the same thing? Do you? Like they are parallel? If you have some particle rotating, and you think of its angular velocity vector and its angular momentum, do you think usually of them as more or less the same thing? No? Okay, well that's good. Because I know some people do. But this equation shows you that they are, in fact, in general, different. The angular momentum and the angular velocity vector are not necessarily parallel. It depends on this I. So note that even if I is diagonal, L and omega are not parallel in general. So this is a point I usually stress, but none of you seem to think that this was an issue, so there's no need. We have considered so far a situation where we have divided this rigid body into a discrete number of subregions. So let's now turn this into an integral instead of a sum by considering a continuous distribution of mass. In which case we should let this mi go to some density function. So it's the density of the rigid body as a function of position. If it's a homogeneous body, then rho of r is just a constant. And similarly, we have to let the sum go to an integration over the volume. So by doing these substitutions, we see that we can write, for instance, Ixx and Ixy in the following way. So you can think of this as a weighted integral over this quantity, r squared minus x squared, by this weight factor, namely the density, the mass density of the object. You integrate over the entire volume. Now, to express this in a compact form, we have to use a bit more convenient notation. So we let x, y, z go to x1, x2, x3, like we did in the previous chapter. If you were to write out the two other components of L, Ly and Lz, you could infer that this is the general recipe for identifying the elements of this matrix of inertia. So this term only contributes for diagonal elements. And this one is kind of nice because it gives you a recipe to calculate the matrix of inertia for an arbitrary rigid body. You only have to know its mass density and also what it looks like, the volume. I'll just add this to be sure. Oops. So we were able here to find a general relation between the angular momentum and the angular velocity vector in a quite compact form, which I have now erased. But we found that L is equal to I multiplied with omega. So as long as you know this moment of inertia matrix given by this and the angular velocity vector, we can calculate the angular momentum of the body. Now, it might seem reasonable to expect that we should be able to find some kind of expression for the kinetic energy of this rigid body, also being related to these two parameters, the matrix of inertia and the angular velocity vector, right? Because they characterize the rigid body, both its composition and its movement. So let's see. Our starting point is the following. As usual, we again consider here the discrete case to begin with. We decompose the body into different subregions. So keep in mind that Vi here is the velocity of region I with respect to the center of mass. So we have this, since we have restricted our consideration to scenarios where we have purely rotational motion. So I've just substituted this for Vi. Now, by using the definition of L that we wrote just 15 minutes ago, you can see that this expression here is equal to 1/2 omega dot L. And so our prediction was correct. We can relate the kinetic energy to the angular velocity vector and L. And L in turn is related to the matrix of inertia and omega. So in effect, the kinetic energy can be expressed through the matrix of inertia and this angular velocity vector omega. We'll take a break there.